Hello students. So up until last class we looked into the topics of tangents, and we also worked out examples based on gradient, divergence, curl. We calculated directional derivative and things like that. And in the last class we started looking into more like differential geometry aspect of vector calculus. So like tangent, normal, binormal, and then we will look into the Serret-Frenet formula. So in the last class we derived a formula for the tangent as r minus small r dot product with cross product with dr dt. So cross product with dr dt is equals to a 0 vector where our r is the position vector, of point P. So if we have a curve like let's say in 3-dimensional geometry, this is x-axis, this is our y-axis, this is z-axis, that's origin. So if we have a curve like this, so let's say this is my point P and this is my point Q, and the position vector of the point P is r. So r is the position vector of a point P, and capital R is the position vector of any point, and capital R is the position vector of any point on the tangent line, and the equation of the curve is of course given by r is equals to ft. So if we want to calculate r is equals to ft, so if you want to calculate the equation of the tangent line, then in that case we calculate for the given curve we calculate dr dt, and then taking the difference of capital R, which is the position vector of any arbitrary point with small r, and then cross product with dr dt will give us the required equation of the tangent to that curve r is equals to ft. Now we can also express this equation in terms of a Cartesian coordinate system. So we are familiar with the equation of the tangent in 3-dimensional geometry to a surface. So we can actually express this equation in terms of Cartesian coordinate system as well. So how do we do that? So we can write r as position vector of OP as xi. So I have told you at very beginning that when we choose r is always x, y, z. So xi plus yj plus zk. So let us write that, and then from here I can calculate dr dt as dx dt. So x, y, and z are the functions of t, and I dy dt j plus dz dt k, or I can also write dx dt comma dy dt comma dz dt. So of course if you can, either it's up to you whether you write in terms of I, j, and k, or you write in terms of as a triplet. All right. So the equation of the tangent line at the point P is given by, so if you remember the last in the last class we derived something like capital R is equals to small r plus lambda times dr dt. So small r is basically our x, y, z, plus lambda times dr dt is dx dt, dy dt, and dz dt. So from here I can write capital R as x, y, z. So I can write capital R as capital X, capital Y, and capital Z, all right, equals to small x y z plus lambda dx dt dy dt and dz dt. Now, from here I will take this triplet on the left hand side, and then we will equate the coefficients of I, j and k from both sides. So, ultimately we will obtain x minus small x by dx dt, y minus small y by dy dt, and z minus small z. So, this should be capital Z minus small z by dz dt equals to lambda, and here capital X, capital Y and capital Z is any point on the tangent line, at small p x y z. So, this is the required equation of the tangent line in terms of Cartesian coordinate system, and you may have seen this type of equation in 3-dimensional geometry for the equation of a line in 3D. So, this is just another form in terms of a Cartesian coordinate system, and for the vector form we know it is capital R minus small r cross product with dr dt. So, now let us work out an example where we see how we can calculate the tangent line at a given point. So, example, find the equation of the tangent line to the space curve x equals to t, y equals to t square and z equals to 2 by 3 t cube, or we can write r is equals to, or don't write or, we will do something about it, at the point t equals to 1, right. So, we have to find the equation of the tangent line to the space curve given by these equations at the point t equals to 1. So, first of all we can write, r as, of course, it is a function of t, equals to f t equals to x t I, y t j and z t k. So, instead of x I can write, or let us write x, y and z, and now I can substitute x as t I, y as t square j and z as 2 by 3 t to the power k, right. And now that we have this equation of the curve in terms of vector as a vector form, I can calculate the equation of the tangent at the point P, or at a point where t equals to 1, first in terms of the vector, and the second we will calculate as a Cartesian form. So, for the vector form, capital R minus small r cross dr dt must be 0. So, that is the vector form equation for the tangent line. So, first of all we need to calculate dr dt. So, what is our dr dt? So, if we like to calculate dr dt, then it will be I, because the derivative of t is 1, then it will be 2 t j and then 3 t square k. So, from here dr dt at t equals to 1 will be 1 plus 2 j plus 3 k, right. So, that is the tangent, and at the point t equals to 1, r t will be, so r t at t equals to 1 will be it's 1 plus 1, so this is I plus j plus 2 by 3 k. Therefore, the required vector equation will be capital R. So, capital R minus the vector. So, this is 1 1 2 by 3 cross product with So, let us write the cross product here, cross product with dr dt. So, dr dt is 1, 2 and 3 equals to a 0 vector. So, if we can be if we want, we can write this capital R as a capital X, capital Y, capital J. So, this is basically capital X minus 1, capital Y minus 1, capital Z minus 2 by 3 and cross product with 1, 2 and 3 equals to 0 vector. So, this is the required equation of the tangent line at the point P to the space curve given by that equation RT equals to this equation, and that is basically cross product with the tangent dr dt equals to the 0 vector. So, this is how we calculate the equation of the tangent line in terms of the in the vector form. Now, we can also calculate it in Cartesian form. So, Cartesian form would be Cartesian form. So, in the Cartesian form, we have to substitute t equals to 1 in dr dt. Then from there, dx dt at t equals to 1 would be 1, dy dt at t equals to 1 would be 2, and dz dt at t equals to 1 would be 3, right. And therefore, the required equation would be x minus small x. So, small x is the point P. So, that is 1 divided by dx dt, which is again 1, and then we have y minus small y. So, that is again 1 which is divided by dy dt, which is 2, and z minus 2 by 3 divided by 3, and where x, y, z is any point on the tangent line at P 1, 1, 2 by 3. So, at t equals to 1, the point P is given by 1, 1, 2 by 3, and that x, y, z is any point on the tangent line at the point this. So, basically we choose x, y, z as 1, 1, 2 by 3, and that is the required and then we substitute for x, y, z here. So, this is the required equation of the tangent plane at the point P, and of course, this is in the Cartesian form. So, either you can express it in terms of the vector form or in terms of the Cartesian form, that is up to you. And yeah, similarly we can find tangent equation of the tangent line for any arbitrary curve. We can have a curve something like x equals to, so this example ends here, but we can have something like x equals to cos t, y equals to sin t, and z equals to t, and let us say we want to find the equation of the tangent line at the point t equals to pi by 2. So, we will follow the similar steps and then use the same formula for the tangent line, and you can be able to calculate the tangent line in the vector form or in the Cartesian form. You can also have something like x equals to t square, y equals to t to the power 4, and z equals to 1, and you are asked to calculate the equation of the tangent line at t equals to, let us say, 1. So, just follow the similar formula what we did before, and that will give you the required equation of the tangent line either in vector or in the Cartesian form. So, the examples would not be that much complicated when you are asked to calculate the tangent line for a given curve. It might involve doing some derivative which may have some higher powers or something like that, but I am pretty sure you can be able to do it. So, now we move to our how to say, a little bit more into differential geometry aspect, but it is not too much differential geometry. It is somehow involving our tangents and normal and the Sennett-Fennet formula. So, keeping those in mind, we have to study these concepts. So, let me introduce that via a small statement. So, basically now we are going to study about tangent line at a point P of the curve r equals to f s, or basically we are interested in unit tangent vector. So, S is the arc length basically. So, S T is the parameter, but when we are using S, it is pretty much understood that S denotes the arc length. So, suppose you have a given equation of a curve in terms of arc length, and from there how we define the unit tangent vector, or first of all the tangent, afterwards the unit tangent vector, we will see that here. All right. So, I am going to state a very important theorem, but we will avoid the proof because the proof is slightly lengthy and it is out of the scope of this course. But interested readers, they can look into the books that I have suggested in the references for the proof. All right. So, the statement goes like this. So, if vector r equals to, of course, vector f s be the vector equation of a smooth curve in terms of S, which is basically arc length, So, S as a parameter, then dr ds equals to the unit tangent vector. So, remember dr dt is in our previous class we learned that dr dt is actually the tangent vector in a way. So, it actually gives us how to say the tangent vector on that curve at a certain point. Now, if we want to calculate the unit tangent vector, technically if we want to calculate the unit tangent vector, then we had to divide dr dt with its magnitude, right. So, dr dt denotes the tangent to the curve r is equals to f t. So, if we want to calculate the unit tangent vector, we must divide dr dt by its magnitude. But this theorem says that if we have an equation r is equals to f s of a smooth curve, then the unit tangent vector will be given by dr ds. So, if we differentiate r with respect to the arc length as a parameter, then in that case the differentiation, the first order differentiation, will give us the unit tangent vector. And therefore, from here what we can write is so from here we can write that dr ds. So, from here this is basically the unit tangent vector, and from here I can write unit tangent vector equals to dr dt times dt ds. So, basically dr dt is actually ds dt times unit tangent vector. All right. So, this is another result. So, that means our dr dt, the original how to say tangent vector, which was not a unit vector, can be given by ds dt, differentiation of this arc length s with respect to t, times the unit tangent vector. So, this is a very how to say a nice result to remember, that the differentiation of the curve with respect to the arc length is the unit tangent vector. Now, from here this formula actually gives us the equation of the tangent vector, where the equation of the curve is given in terms of s. So here we see that the equation of the curve is given in terms of s, and in this case, and basically the tangent vector can be calculated as ds dt times the unit tangent vector t. All right. So let us see how we can calculate this unit tangent vector unit tangent vector t cap. So I can start with an example. So first of all, suppose the given equation of the curve is x equals to t, y equals to t square, and z equals to t cube. So that's the given equation of the curve. We have to find the equation of a unit tangent vector. So either we can calculate dr dt and then divide it with its magnitude, or we can use that previous formula. So I can write from here, I can write r is equals to ti t square j plus t cube k. So this I can always write, because I can write xi, yj, zk. Now from here, my dr dt is basically I plus 2 tj plus 3t square k. So that's my dr dt. All right, and we know that from previous formula, dr dt is basically t cap ds dt. All right, so ds dt times t cap. So that I have written here. Therefore from here, dr dt mod is equals to mod of t cap mod of ds dt, isn't it? Now mod of t cap is 1 because t is a unit tangent vector, so its magnitude is always 1. So we have mod of ds dt, and therefore mod of ds dt, and therefore from here mod of ds dt is nothing but mod of dr dt, and that's basically 1 plus 4t square plus 6t to the power 4, isn't it? And now I can write this here as t cap. So the tangent vector is t cap dr ds, and dr ds can be written as dr dt times divided by ds dt, because this can be written as dt ds. I will bring it in the denominator, and then it will become ds dt, and if it is in denominator, then ds dt is this here, and therefore dr dt would be ds dt is basically the mod or the positive value. So it will always remain positive, and dr dt would be I plus 2 tj plus 3t square k, and mod of ds dt, that means taking only the positive value, 4t square plus 6t to the power 4. So this is our required answer, or the value of the unit tangent vector to the given curve this here. Of course, as I said, we could have divided this. Wait, it's not 6, it's 9 actually. Yeah, 9. So we could have divided this dr dt with its magnitude, and that would have given us the unit tangent vector. But in case if you didn't have t, and if you had arc length s as x equals to, let's say, some s, y equals to some s to the power 3 or something. So that means the given equation is in terms of the arc length, and then we had to use a different formula to calculate that unit tangent vector. And if you have something in terms of s, then basically the derivative of that r with respect to s would give you the unit tangent vector. So the unit tangent vector, the curve, and the arc length is related in that with that relation, that t cap equals to dr ds, and it's also a very important relation to remember. All right, and now that we have introduced the concept of unit tangent vector, we can move to our next topic, which is normal at a point. So normal or normal plane at a point. So, normal or normal plane at a point. So, what is the definition? The definition is the plane through a point P, the plane through a point P perpendicular to the tangent at P is called the normal plane. At that point, all right. So, usually that is what we mean by normal. So, you have a curve and then you have a tangent at a certain point P. So, a line which is perpendicular to the tangent at that particular point is called as the normal to the curve at that point. So, usually a normal plane is like a generalization of the normal to a curve. So, if you have a plane that is passing through a point P and if it is perpendicular to the tangent plane at the point P, then that plane is called as a normal plane to the given surface, or in this case to the given curve at that particular point P. All right. So, let us see how we can express its equation. So, we know that the equation of the tangent plane is given by capital R minus a small r. So, this we know, capital R minus a small r dr dt equals to 0. So, this means that these two vectors are parallel, right. So, dr dt and capital R minus a small r are parallel to one another, and therefore, their cross product is 0. So, if I write capital R minus a small r dot product with dr dt equals to 0, then capital R minus a small r is perpendicular to dr dt, and that will actually help us to obtain the equation of the normal plane. So, if R denotes the position vector of any point on the normal plane at the point P, whose position vector is small r, then the vectors capital R minus a small r and dr dt will be perpendicular to one another, that is capital R minus a small r dot product with dr dt equals to 0. So, dr dt is basically the tangent vector, and if we choose capital R as any point on the normal, which is normal at a point P, then in that case capital R minus a small r will be perpendicular to dr dt obviously, and therefore, that equation capital R minus a small r dot product with dr dt is basically the equation of the normal plane, because dr dt and capital R minus small r are perpendicular to one another, and that is actually what normal plane mean, that a plane which is perpendicular to tangent vector is actually a normal plane at a point P to that curve. So, this equation is actually the equation of that normal plane at a point P to the curve r is equals to f t. All right. So, this is the equation of our normal plane. So, in today's lecture we saw how we derive the equation of a tangent plane at a point P. We worked out few examples. We also gave the concept of a unit tangent vector, and we derived the normal at a point P to a given curve. In the next class we will start working with some examples, and I will also try to introduce the concept of unit normal, and if time permits the concept of binormal. So, I will stop here for today, and we will continue with our next topic in our next class. Thank you.